This is recording number 6 on chapter 7. Mm-hmm. Yeah, and this one, there are several examples here. I mean, they all pretty much follow the same principle of what we're doing. But this one in particular, what it's trying to show you is that you have to load your beam with different cases in order to determine your maximum moment. Mm-hmm. And so the beam is given, right? And of course there is the different loads that you're going to use, right? There is a weight beam here that has been already included in the calculation. The live load. The epsilon t that I'm recommending is the 0075, just to see what happens there, right? The gray 75 is the yield value you're reinforcing bars. So this is not your regular 60. Okay? And so we'll see how that works. Okay. So first you need to find then your MU, right? Oops, I don't know why I go there. How did I get there? That's interesting. Okay. So first thing then is MU, right? So you need to find MU, and this is what we're trying. So we start first here and loading my del loads. Mm-hmm. And this is normally how you will set it up in your computer software. Okay, you load the loads. Then your live loads have different cases. There is one case where you load the whole beam. There is another case where you load one span. There is another case where you load only the overhead. So your live load has like 3 different cases, right? And so for each case, you find your bending diagram. Of course, you will find your shears too when you're doing shears, right? And you have all the diagrams, and then you combine the moments, right? Rather than combining the forces like we were doing before, right? You multiply your load 1.2 D plus 1.6 L. Now we're going to do the same, but we're going to multiply the moments. So this one is the load. So there are 2 moments for the load, one positive and one negative. So we multiply those by 1.4. That will be one load combination, and that will be the maximum for this load combination. The other load combination is your 1.2D, 1.6L. So you're doing a software, then the software will do exactly this. It will take 1.2 times your moment due to the load, and so it will be the 124.2, that positive, and then 1.6 times the largest moment on the live load, that is positive, and that's your 200. And so it will do that, and it will give you this value. Yeah? Then for the negative, you will do the same, the 1.2 due to the load. Okay. And then you will find the largest due to a live load is the same, 72. So we use 72, and that will give you then your maximum factor moments. Yep. The epsilon t here, I didn't change this. Oh yeah, equal or better than 0075. Okay, that's good. So I'm going to pick a value of 0.01. Okay? And that will be better than 0075. So this formula, right, it is in your design aids, but it's not in the ACI code. Okay? So this is in the design aids. So this is where you find it. Okay? And let's double check. Just to make sure. Right? I mean, it should be in your design aid. There it is. Right in the front. I mean, right there. Okay? So there's the formula you will use for this type of problems. Okay? So right there. So remember, that formula is not in the ACI code. Don't even try to look for it there. It is here in your design aids. All right. So we got the formula. We are going to replace the epsilon t, right, by 0.01. Find our raw value. Then we set up the inequality, right? We replace the parentheses by 0.9d. We replace the area of steel by rho BD, and that now gives us a formula in terms of BD squared. And with that, we set up our table, and we start finding the different B's and D values, right? For this case, I decided to select 18 and 24. Okay, that gives you about a 1.5 ratio, right? So we do that. You add the 2.5 for a single layer. That's 26.5, say 27 or 28. I will pick 28 because if you go by even numbers, it's easier to form. Okay. Okay. Check your minimum H. Since you have a cantilever section, that will be L over 8, right? This one right here, we have one end continuous, so it will be L over 18.5. So we do that. Now we have a reinforcing steel that is 75, so it needs a correction. So we find the correction. The correction factor is 115. So we multiply the 13 by 115 because 13 is the controlling minimum, right? And that gives us 1495, which is less than 28. So we're good. One comment about this, remember these 9 and 13 are your minimum values. 13 is your minimum value. Okay? So you are not looking for that 20% increase or anything like that. These are your minimum values. In the quiz, I asked for the minimum value. I didn't ask for a design value. I asked for the minimum value. And so you should have picked up just the minimum value. In this case, for the whole beam, I will use 13. But in this case, corrected, it will be 15. Okay? So my minimum value will be 15 after correction. But that's my minimum value. Okay? My beam 18 by 28, check my weight. Is very close to what is assumed, so we're good. Find the required area of steel, find my approximate D, find my area of steel, rho times B times D, that's 363, check for minimums. These formulas are in your code, and so also in the design aids, so you can use that. Okay, so we check minimum, control by 122, and therefore we satisfy minimum. Go to the tables, we get 3 number 10s, there is the area and the B minimum, right? The area and the B minimum, and I already showed you this several times, so you should be able to know how to find this. Yeah? 6 number 7s also work, and so I picked 6 number 7s. Okay? You could have picked, for construction purposes, remember, the least bars you can use, and as long as you satisfy cracking control, that's a better choice. So 3 number 10 would be good for construction. 6 number 7s will be good if I'm trying to control the width of the crack. Right? Okay, so I'm using 6 number 7s. Find now my actual D's and D sub T's using the bars that I have selected. Find my A value using the selected area. Right? Find my C. Check for the ductility. Right? We got an epsilon T of 0.0119. Okay. Oh, this is the wrong version. So, sorry. So I think we need to load the correct version. All right. Let me see if it's true. Yeah. Okay, correct version. Where are you? Okay, let's see. All right, there it is. This is supposed to be the correct version. Okay, so this part doesn't change. It's the same. We're the same here. 24, we're the 28. It's all the same. This is the same. And so we find our value of epsilon t. Now for grade 75, we need to find our strength for tension control, and that's 0.003 plus epsilon ty. So my epsilon ty, right, which is your yield value, is simply your Fy divided by the minus of elasticity. That's 0.0026. So the limit then is 0.0056. Our value is definitely higher than that. So we satisfied A is maximum. We satisfied the fifth factor of 0.9. Okay. Next, we check the design flexural strength. Right? Same formula that we used for quite a while now. And things are satisfied. Okay. So it's good. Then when we come to the negative moment, right? When we come to the negative moment, what happens? We're not going to use the same approach as the epsilon t. Why? Because you already have a section. You already pick one. Okay? So then this problem right here, the negative moment, is a problem now like procedure A, right? Designed when you know the section. Okay? So your section now you know is 18 by 28, so you know. All right? So we're going to do that, and so since we know already the D value because we calculated it here, right? Our D value was 25.7, so we can just replace it in there, find the area of steel, right? And with that area of steel, we get check against minimum. We already looked, we had the formulas already for minimum, so we don't have to do this again, right? We just pick the same value, right? And then we find our A value. With the A value, right, we are going to find a new area of steel, and the new area of steel is 127. It got very close to the minimum, but still greater, so we're good, right? And then we go to the tables and look for numbers, right? Here is the 7 number 4s. One thing about grade 75, grade 80, grade 100 is that you have to call your supplier and make sure that it's available. Okay? So in this case, you say number 4 is not available. So okay, no, we cannot use that one because it's not available. So that leaves us only with this option. So we use 3 number 6s. Okay. Okay. So we're going to use the 3 number 6s. So this is not the same as the 7 that we're using for the negative. Therefore, we are going to change our D value now. So this is our new D value. And then we're going to find our A, again, our C value, our ductility again, using the correct D value. And compare that number against the value for grade 75, which we already found. No need to find it again, right? And it's satisfied. So that means A is maximum satisfied, phi factor of 0.9 is good. So we find our strength value, and we got 185 versus 180, that's good. So we got then 3 number 6s on the negative, 6 number 7s on the bottom. Yeah? And those are your two designs. Notice tension on the top for the negative, bars on the top. Tension on the bottom for the positive, bars at the bottom. Okay? All right. Here's another example. In this example, I mean, all we're doing here now is, again, changing loads, different cases, but the procedure is already the same. All right? Here I want you to maintain the epsilon t between 0.006 and 0.075. We are back to 60 in terms of the strength of the rebars. Beam weight is being assumed already as 0.50. So it's telling you to assume that weight at the beginning. So we're going to see that. And so, beam weight, it says assume that, so we start with that one, right? Find the required moment, mu. And again, low combination controlling is 1.2, 1D, 1.6L. We multiply the 1.2 times the 0.8 given plus the 0.5 that we were told to assume, right? He says add, right? To these loads, you're going to add a 0.5. So, okay, so we added the 0.5. The live load is there, 1.3, 1.3. And you also have point loads. Okay. So this one then gives me my uniform load. The point loads have to be done separately. We have both dead loads and live load point loads. So we do the combination, we get 44. Now we find our moment, right? So because this is cantilever, you look at your tables of bending, right? Bending formulas. And the moment due to the uniform load is WU L squared over 2. The moment due to a point load is simply the load times the distance. Load times distance, right? And so that's what it shows here. Okay? WU L squared over 2, load times distance. So we do that, we get our moment. Then we go to our magic formula here, right? Assume a value of epsilon t. Well, they told us to be within this range. So I picked 0.007. You could have picked 0.0072 or 0.0078, whatever you want. But that's what I picked. So I get my raw value, check for minimums. This one controls, we satisfy the minimum. Then we set up again the creation of the table, right? And you know how to do this now. So you do that. Select a combination. For most cases, I'm trying to be on the 1.5 to 2. Okay? But really, I mean, all these combinations work. So pick 16, D value 24.4. I added 2.5. That's kind of 27. As I said, I don't like the odd numbers, so I went to 28. Okay? Check my H minimum. This is a cantilever beam, L over 8, right? Table 9311, right? That's where you find it. So 12 times 20 by 8, that gives you 18 inches for the height, and we're using 28, so we're good. Check beam weight, 0.47, 0.50, that's good enough. Find the actual area of steel and the D's. So you assume your D, find your area, then go to the tables and select bars. Notice that I need 7 number 9s. Doesn't fit in one layer. This one coming doesn't fit in one layer. So we have to use double layer. Okay? Or we will need to increase the width to at least 20. So we have to go to this combination. Right? Let's try the second option. So I'm going to go then to the 20. So now you got 20. My age will be 21.9 plus 2.5. That's 24.4. I have to run it up, right? So I say 25. I don't like, again, odd numbers. So 26, all right? 26, definitely greater than my minimum. It was 18. We already found it way back here, right? And so that has been checked. And so we are good, okay? So we have it here, right? 18. So that's, we have it. Okay. Check bin weight, 0.54, 0.50, close enough. Well, pretty good. Remember, I mean, the really a 50% change in weight, 50% change in weight will only change a moment in the order of 5 to 10%. You keep that in mind, then all you have to do is find a moment that is larger than what you need, and that satisfies your requirements, right? All right. So check bin weight right here, find actual D. So now I say, okay, I need 799. A number 9s require 2185, so doesn't fit. But 5 number 11s will fit in 20 inches. A number 9 would require a double layer. So it's possible solution, but you have double layer. So 5 number 11s has a slightly less area than what we need, right? Because it says that we need an area of what, 799, and this is 780. Okay, should we go with a lower area? Well, that depends, right? Depends on what? Depends on how you selected your age, right? So we go back here where we selected the age. For this combination to work, my age has to be, is that the age that we did? Something is not right. I'm looking at something is not right. That's why you see me stopping. Oh, the bin weight is not right. Yeah, because this is supposed to be 28. Okay, so, but we picked this one. We needed 26.9. So if I pick my height as 27, I don't have much room. I mean, I pick exactly pretty much what I needed. So my area has to be pretty much what is required. But since I went to 28, that means I added a little bit more height. If I add more height, I may not need the same amount of steel, right? And so maybe going from 799 to 780, which is not a big difference really, right? Might work. So we're going to try it. Okay? But let me change this one right here before I forget. So that's 28. And therefore we got 20 times 28 divided by this 144 times the 150 and 20 times 28 divided by 144 times 150, and so it gives you 58. Okay. So this is really 58. No? No. Do I need to check my moments? Do I know? No. Remember, the change is not significant. Okay? All right. So we're good. So 5 number 11s. I'm going to work with those. My actual D now with the 11s is 23.3. My raw value, of course, is that now is greater than the minimum, so we're good. Check for my A value, check for my ductility, right, using the right 23.3. My C value, which is 689, and I got 00715, right, and that value is within the two numbers that the problem was asking, right? And in both cases, I mean, since this is grade 60, right, we have satisfied A's maximum and the phi factor of 0.9. So then we put it here in the equation, and we got 8,654. Now, there is one thing that I said, I mean, it's greater than mu, but which mu, right? So let's go here. The last mu that we found was this one, 7,897. Okay, 7,897. That was with this weight that we added of 0.5. 7,987. But we have 8,654. Right? That's more than 10% increase. So that little change here in your weight, right, from to 0.58, is not going to do anything. All right? So you're good. Check cracking control. I got my B value. I remember using number 11s, so we multiply times 2 the diameter of the stirrup. That's your B value. And so we replace the numbers here. The cover, stirrup. Again, this is not right. Okay. 0, right? Because that's what we have. Because it's number 11. I mean, only 14 and 18, you would actually use the diameter of the bar, but not for this one. So 1.5 plus 0.5 plus 1, right, equals times 2 minus 20 and divided by 4, so 3.5. Now why are we divided by 4? Then this is done with the previous, oh yeah, we got 5 bars, right? 5, 11, so yeah, so we got 4 spaces. So this is giving me 3.5. That's interesting. Let me have a check that. So 2 and 3, yeah, 2 and 3, 6, 24 minus 6 is 14, 14 divided by 4, yeah, 3.5. 3.5, right? So that's the spacing that you have. The spacing that is required, right, for grade 60, right, is C sub C here, which is all the way to the bottom of the bar, in this case from the top because you have tension on the top. It will be 1.5 plus 0.5, that gives you 2, and so they give you 10 inches. And then this one is always 12 inches for grade 60. So yes, we satisfy that. The height is less than 36, so we don't need the skin reinforcement. Okay. Right? So no problem. Let's look at this one. Same thing. I mean, now we got some point loads in here. 5,000. Again, I mean, all these problems, all I'm doing is changing the load position, the type of load, so you will use your different formulas for bending. But other than that, the design method is the same. Okay, assuming weight. Okay, I can get it from my table of weights, so you just assume weight. Okay? Remember, an error in the weight of about 50% only causes 5 to 7.5% increase or decrease in your moment. So any guess really is pretty good. If in doubt, pick 0.4, 0.5. Okay, that's normally good number. All right, so 0.2. So I get 0.2. So that would be the only uniform load. Because I have live loads, I have to use 1.2 and 1.6 combination. So I go 1.2 times my weight of the beam, and then 1.6 the point loads, and they give me that. They keep it separate because they're different kinds, and I find my moment as what? Due to the beam weight is WU squared over 8, and due to my point loads is PU times A in this case, so I get 36. Okay. Assume an epsilon t 0.008. Remember that because it's grade 60, any number above 0.005 is acceptable. So you have lots of designs. And there is no restriction here, right? So I pick this number, you may pick 0.01, somebody may pick 0.015, okay? So lots of different solutions, not one solution here. So you get the same solution in this problem, right? If you give me the same solution as your friend, I will see your body count, okay? Because there is no reason, absolutely no reason to pick the same value. All right, so we put a 0.008 in the formula, get the amount of steel. Again, with that, we're going to set up the inequality, replace the parentheses by 0.9D, replace the area of steel by raw BD, create a table, and notice that in this case, we didn't have very many choices. I mean, this is already pre-narrow. I mean, 8 inches, right? And it's 849. So if we go to 10, it's going to be even less, so it doesn't work. So let's try this B8, right? And B8.5, add one layer, that's 11, make it 12. Check the minimum age. Oh, the minimum age for this beam is 15. So I'm going to use 12. I have to use 15. Yeah? Again, with me liking even numbers, I go to 16. Okay. Check bin weight, less than 0.2. So we're good. Okay. If you want to create new moments, you can do the new moments with the less weight. So there it is, 32. Okay. And what do we have? 36. Right? So you are looking at 32. Your moment is almost, your weight has changed almost half, right? From 0.2 to 0.1, right? Pretty much. And your moment only changed from 36 to 32. Right? That gives you an idea of how much that beam weight will affect that. Right? There is no need to find dimensions again, simply because what? Why? Ah, yeah, I know. You knew it, right? Because you're using H minimum. So the table is not controlling your H. The H minimum is controlling your H. And because of that, right, because you were controlling your H, the H minimum controls the H, then you don't have to worry about the table anymore, right? So then I had to use my 16 minus 2.5, 13.5, find my raw value, 166, yeah. Check my A, check my area of steel. Right? Now, why am I doing this here in terms of the area of steel? Why am I not using this? Okay, this is kind of deviating from our method, right? The reason for that is that the table, right? The table does not govern your design. The minimum is governing your design. Now you're using an H that is a lot bigger than what you needed. So that means that the area of steel, right, that you assume here is probably too much for what you need because you are adding more height. Okay? And so that's why I did this, where I'm going to find my own area. Then I do a new A, and I recheck my area, and I get my area now. And so that gives me now a 2 number 5s. The minimum 6.9, I have 8.5. So that's good. Find my actual D, check my minimum again, because I have reduced my value, right? My area has gone down from what it was to this new number. So I need to check my minimum. And I got 0.0056, minimum is 0.0035, so that's good. Okay, so we're satisfying minimum. Find my A, find my C, check ductility, 0.027, And you said, but you assumed 0.008. What happened here? Why are you getting this 0.027? A lot more than what you assumed. Why? Because you have a larger age, right? The table, which is based on the 008, is not governing your design. It's H minimum that is governing your design. And therefore, you added more height than what you needed, right? And if you add more height, you need less steel. And if you put less steel, you're moving to what side of the graph, of that phi factor graph? To the left, to the right? Yes, to the right, right? You're moving to the right. You're moving closer to the minimum. And that's why your ductility is pretty high. Right? All right. And so that satisfies my ductility. That means it is maximum satisfied, phi factor satisfied, right? Now you can just see over D sub t you want to. Then check my capacity. Then you check that because they can change a lot of stuff, right? So notice that, yes, this one becomes 37 and this is 32. So we're good. We're good. Amen. Notice that this value even satisfies the original weight, right? The original weight was with 36, so even that is still satisfied. All right, and that's tension at the bottom, so you put your bars at the bottom and then there. Here's another case. This one again, just to show you, that you have a negative moment here, you're going to have a positive moment here in the middle, and a negative moment here, right? And you kind of done already this. You've done this in one exam, so you know that. So, design the largest possible section using a width of 14, right? And you're going to sketch the final solution, and there is your properties for the material and your loads. Right? So, largest possible section. That means using A is minimum, right? A is minimum. Okay, so let's do the load combination, 1.2D, 1.6L control. You have uniform loads, you have point loads, you find your moments. This is the moment due to the negative uniform load. This is the moment due to the positive uniform load. The value for the moments at 16, right? At 16, okay, so now why is 16? Oh, the load that is at 16, so this load. The load that is at 16, the moment due to this load, right, at the left end is this one, and at the center you need to find that value, and it's this one right here. At the right end, the effect is this one. Right? So this is the moment on the left support, the positive moment, and the right support is in negative. Right? Now, for the moment due to the other load, the load at 4, right? I'm going to flip the numbers, right? Because symmetry, right? So I'm going to flip the numbers, and so I'm going to have at the left end, instead of having the 553, I'm going to have the 2212. At the right end, instead of having the 2212, I'm going to have the 553. The middle value should be the same. And so now when we add up moments, this is the negative moment, right? And this is your positive moment. We check for row minimum, and so that's what we're going to use, right? And we put that in this right here, so we can create a table, but there is no table. Why? Because they told us that the B value has to be 14. So that gives me a D of 36.4. I add 2.5, that's 38.9. Oh, so here's this, okay, 39. So that would be 39, right? And I would say, well, I go to 40, right? Because Diaz likes to have these even numbers. And so 39 becomes 40. Wait a minute. What is this H? That value, 38.9, is the largest value you can use with a B of 14. So that means you should not go above 38.9, right? Because then you will be violating your minimum requirements. So you need to round down. So your minimum should be then 38. Okay, so I'm going to do 38. Okay, so this is not right. 38.9. All right. Represents the maximum height. So you need to round down. Okay, check minimum. Minimum should be okay in this case, right? But we check it. Okay, L over 21, this 11. Well, we're using 38, so we are pretty good. Check beam weight. Close to what we assume, so we're good. Find required area of steel. So there is your new D. Find your area of steel based on minimum requirements, 166. 3 number 7s will do. It fits in the width of 975. We have 14, so we're good. Find the new D. With the new D, you can check your minimum in case there was a mistake someplace. That's good. And then you're going to check your A, your C value, your ductility again. Make sure we got the right numbers, 35.6, yeah. Ductility 0037, right? And so that's pretty good. And greater than 005, which is for the value for grade 60. So you have satisfied A's maximum and your phi factor of 0.9. No need to find a formula for A's maximum. So 3 number 7s on the top for the negative moment will work. Check the design strength, and it is pretty good. All right. Now I'm going to design my positive moment, right? So how much is my positive moment? Let's go back here. This is 119. But to design this one, right? The 251, I have used the minimum amount, pretty much. Very close to it, right? So 119 is a value way below that. It's going to give me an area that is even less. But I cannot go below my minimum, right? I cannot go below my minimum, right? So we can do a little thing here. Let's see how that works. How much, but we need to check all these ductilities, okay? Yeah, to make sure. So, since we have used, right, a minimum area for the negative, then we use the same for the positive, because we cannot do anything else, right? We cannot go below the minimum. So there it is, right? No need to decide. No? I know you were panicking already. You said, I will put that in the exam. I have to do 5 pages. No, because see, that's the same. You have to do more work. But because you got 38 though, we had to put a skin reinforcement, right? For the negative and for the positive. So you had to put it in both. You had to come down this way, you had to go up this way, right? So use 6 number 3s on each side, right? Equally spaced. S less than 6 inches. Negative and positive. So all the way up. Same thing. Mm-hmm. That to satisfy your value for cracking control. Mm-hmm. And why we're doing 6? Well, this is based on what we found before, right? The minimum usually is 12, or a little less than 12, maybe 10 or 8, right? And that's about it. That's all you can get out of the formula, right? For cracking control. And so 6 is pretty good. I mean, that would be less, and it satisfies the requirement. So let me go back to one of these formulas here for cracking control that we use. Just a minute ago that we use it. Okay, right here, see? I mean, this value 2, right? Because that's the only thing that is changing here, right? The worst it can be is they say, okay, my cover is going to be 2 inches, so now I got 2.5. So then it will be a little smaller, right? But maybe you would get what, 8.5 or 9, right? Not much, right? So an S of 6 inches will work. Right? So that's how you can simplify your time spent on a solution. You have to understand those things. So don't forget, I mean, the worst you can have for a beam. This is for a beam, okay? For a beam, the worst you can have maybe say 2.5. So you get that then 15. So you're going to get 15 minus 625, and so that gives you 875. See? Let's say you have a cover of 3.5. 3.5. So now your spacing is going to be 625. I mean, 35. So a spacing of 6 inches for beams, right, on the face is pretty good. All right, it's pretty good. All right. Good. So that will help you simplify lots of calculations. What else is here? We have one more problem here. Redo example 727, but using grade 100 reinforcement. So 727. Let's see what 727 was. Okay. So it's this one. It's the cantilever one, right? And we're going to use simply grade 100. So that means that this is the same. The loads are the same, right? What is going to change, and this is where the problem is going to be right in here, right? So let's see. So 7. All right, so we've got the same, all that is the same. So we assume again 0.007, right? Happy, right? You do that. You use your formula for minimum, that one controls. And so we satisfy minimum, put it in the formula, right? And then we have all these combinations. All these combinations will work. Now, the use of a higher grade of steel should result in less number of bars. So let's try, instead of 16 that we used before, let's try 14. And D 26.1, and so we added 2.5, 26.6 again, that will run to 29, so we'll go to 30. Okay. Check my H minimum. H minimum is satisfied. Check weight, close enough, right? Approximate my D, find my area of steel, look for my bars. They fit here. 4 number 9s fit well in 14, so we do that. 4 number 8s also fit well, barely, 1405, so not good because of the stirrup, right? And so we're going with the 4 number 9s. Actual D based on number 9s. Check my minimum just in case. Find my A, find my ductility again, my C value, all that. 0068. right? Here we need to find the limit for tension control. I need my epsilon ty, so I find 0.0034. Oh, I add to that is 0.0064 and 0068. Oh my God! I'm almost dealing with what? With the smallest possible cross section that I can have with the 100 steel. Right? So what D tells you is that even though the limit, right, picking up a value of 0.0075, 0.007, which was good for grade 16, it cannot be good for grade 100 because you're moving your point to the right, right? And so for 100 really, I mean, you want a larger section, you will have to start here. You will probably want to use a 0.01. But the problem has the constraint that we have to be between two numbers. So in that case, then that's all we can do. So we do that, and we barely satisfied. I mean, we're pretty close to that, and this happens to be the tension control value. So we're still satisfied. So A is maximum satisfied. Phi factor is okay. Check the capacity, right? Satisfy capacity, no problem. And check cracking control. Check the spacing. Okay, we're putting 4 bars. So we do that. I don't know why I keep doing this. B value here. I like to do that. Yeah. I think I was copying something. This should be 1 again. So that would give me again 2, 3, so 6, 8 divided by 3. So 2.67. All right. Again, I mean, the maximum spacing permitted. Now that you have a 100,000 here, notice what happened to your spacing. Remember that with grade 16, we said, oh, about 8 inches is, that's very good, right? 6 inches you can select. Now look at what happens with 100. Whoa, you went down to 4. You cannot exceed 4. So very important to understand the behavior from going from 100 to 60, right? 60, 100, right? 30 is less than 36. We don't need the skin reinforcement. Okay, that's kind of close, huh? Not bad. All right, so we'll stop here since this is a new topic.